Hi everyone, now we are at lecture number 13, sequences and series. So start with theory number 10, Cauchy's nth root test or simply root test. In the last class we have seen ratio test, right? D'Alembert's ratio test. Now it is a root test, Cauchy's nth root test or root test. So the first requirement is let an be a series with an more than or equal to 0. That means the terms are non-negative, first requirement. So here the first requirement is an is more than or equal to 0 for n more than or equals to n. After certain stage the term should be more than or equal to 0. The first few terms are negative. We need not worry about that. Okay, because it says that after certain stage the term should be more than or equal to 0. That is the requirement. Okay, for Cauchy's integral test. And suppose that limit n tends to nth root an. That's what the heading is, Cauchy's nth root test. Nth root here, nth root. So nth root of nth term actually. Okay, the name itself says nth root of nth term. If the limit value is L, then the first conclusion, the series converges if L less than 1. And the second conclusion, the series diverges if L is more than 1. And third conclusion is the test is inconclusive if L is equal to 1. If the limit value is equal to 1, we cannot conclude the convergence or divergence status of the series. Then we can proceed to the other test if L is equal to 1. If L is less than 1, then L is more than 1, then only we can conclude by using this Cauchy's nth root test. Okay. Again, the proof is not required. Just have some problems related to this. First problem, find the convergence status of the series n is running from 1 to infinity 2 to the power of n upon n square. So how to recognize the problem belongs to Cauchy's nth root test? Simply, if power n terms are present, if power n, for example 2 power n, okay, or n power n, or n plus 1 whole to the power of n, like this, okay, or ln whole to the power of n, ln whole to the power of n, like this. If the power n terms are present, power n like this, then you remember the Cauchy's nth root test is most suitable method. You can apply any other test, no problem, but Cauchy's nth root test is most suitable method. Okay, power n terms are present. Look at here, 2 to the power of n. So power n term is present. Then I am proceeding to the Cauchy's nth root test. So clearly, what is an now? An is 2 raised n upon n raised to. Okay. Now I want what is limit n tends to infinity nth root of that nth term of the series, which is, so limit n becomes large. Okay, limit n becomes large, nth root of what is an? 2 raised n upon n raised to. So this is nth root of this. And if you simplify this, you can write this one like this also. Limit n becomes large. 2 raised n upon n raised to whole power 1 upon n I can write, right? Because it is nth root 1 upon n. Okay. Then you send 1 upon n to both numerator and denominator. So 2 to the power of n whole to the power of 1 by n divided by n square whole to the power of 1 upon n. Like that. Okay. So limit n becomes large. Okay. So 2 to the power of n whole to the power of 1 upon n. I am applying the power both numerator and denominator as well. So and n square power 1 upon n. We are applying the power both numerator and denominator. Okay. Now simplify. So limit n becomes large. So look at this, n and n cancel out here. This n and n cancel out. Only 2 will remains, right? Only 2 will remains divided by here n to the power of 1 upon n I want to write, and whole to the power of 2 I am writing. I am interchanging the powers. Again it becomes same, right? Yeah. So then apply the limit to both numerator separately and denominator separately. So limit n becomes large 2 divided by limit n becomes large and denominator is n raised 1 upon n whole raised 2. Okay. Now look at the numerator value is just 2 only. But look at the denominator, limit n tends to infinity. What is n power 1 by n value? Already I done this. look at once. Since limit n tends to infinity, n to the power of 1 upon n. This problem already I did in sequences. Look at once. I got answer 1. Check once. So by using this result, so how to prove this? Simply you take this one is some a n is equal to n power n by n, apply both sides natural logarithm function, and then proceed. Already done this. Check once in sequence topic. Okay. So therefore, this value is 1, so 1 square, right? So 1 square, because this limit value is 1 power 2. So finally, how much you got? 2. But 2 which is L, but this is what? More than 1, right? According to theorem statement, look at the theorem statement. If L is more than 1, second statement, the series diverges. So therefore, clearly here, so therefore by, so conclusion is, so therefore by Cauchy's nth root test, or simply nth root test, by Cauchy's nth root test, the given series is, the given series is diverges. That's it. Diverges. Okay. So let me write two notes. So note number 1. First note. Okay. If factorial terms are present, in the series, then ratio test is most suitable. Okay, then ratio test is most suitable. Okay, most suitable, right? And second one, this one, if power n terms are present, power of n terms are present in the series, then nth root test is most suitable. Okay, so these are some tricks for these two tests. So this you make a note. Yeah, so by looking at the problem we can realize that. So if nth term and factorial both are present, that I will tell you by one of the problems. Okay, yeah, look at continuation. Next problem. Find the convergence status of the series n running from 2 to infinity 1 upon ln n whole power n. Look at power n terms are present. Then most suitable method is Cauchy's nth root test. Okay, so now what is an? An is 1 upon ln n whole to the power of n. Okay, now limit n becomes large, nth root of an. Okay, which is, so limit n becomes large, right? Nth root of, or simply, so nth root of 1 upon ln n whole to the power of n. Okay, then you simplify this like limit n becomes large, right? So 1 upon ln n whole to the power of n power 1 upon n I am writing. This nth root I can write 1 upon n. Then send 1 upon n to both numerator and denominator. So therefore 1 upon 1 to the power of n is 1 only. Denominator ln n whole power 1 upon n is simply ln n only, right? and limit n tends to infinity 1 upon ln, so 1 upon infinity, that is 0, 0, and which is L, right? So which is L, and this is less than 1, satisfied. So therefore conclusion, by nth root test series converges. Converges means the sum is finite. How much we cannot tell by using Cauchy's nth root test. Cauchy's nth root test will give you only whether the sum is finite or not. That's it. So here converges means sum is finite. So if you do all the sum from 2 to infinity, all these terms, you will get a finite number. That's it. Okay. Next continuation, problem number 3. You look at this, similar kind of but different one. So again, an is n raised to upon n plus 1 power n raised to. Okay. Now since power n term is there, so I am proceeding for nth root test. So limit n becomes large. Nth root of an is, so limit n becomes large. So nth root of that, so n power n square upon n plus 1 power n square, whole power nth root means I am writing 1 by n, 1 by n. Then simplify this. So limit n becomes large, so n power n square whole to the power of 1 upon n, upon n plus 1 whole to the power of n square and whole to the power of 1 upon n, power 1 upon n. Now this limit n becomes large. Okay, limit n becomes large. Let's look at this one. So 1 n square, so 1 n will be cancelled out, right? So then n power n only will remains in the numerator. Okay, divided by, here also 1 n will get cancelled. So n plus 1 whole to the power of n will remains. Okay, next what to do? Our main goal is to find the limit of this value. Whatever the method you can apply. You can apply squeeze method or sandwich theorem or squeeze method, both are same. Whatever the technique you apply, the thing is we need to find this limit value. Our goal is that. Okay, so then this I can write limit n becomes large, n upon n plus 1 whole to the power of n. Okay, yeah, so this can be written, which is limit n becomes large, right? Look at numerator, I am writing as 1, and this n I am bringing down like this, so n plus 1 by n I am writing. Can I write? Look at numerator n, I am bringing down, so it becomes as n plus 1 by n. If you simplify this, again n will goes up. Okay, and whole to the power of power n. Okay, and this will be limit n becomes large. Okay, 1 by 1 power n is 1 only, so n by n is 1 plus 1 by n. I am simplifying inside and whole to the power of n. That power n I am applying for both numerator and denominator as well. Okay, 1 power n is 1 and n plus 1 by n whole power n. But n by n is 1 and plus 1 by n I am writing like this. So this is a formula again. You know already this one. Since by using limit n tends to infinity, this also I proved already, 1 plus x by n whole to the power of n. How much it is? It is e power x. So by using this formula, so this will be how much it is? 1 by e directly. Send limit n tends to denominator and both numerator. So numerator value will be 1 and denominator will be e. X instead of x we are having 1, so it is e. So this is nothing but 1 by 2.73. So this is less than. So this is L value, isn't it? This is L value which is less than 1. So therefore conclusion, by Cauchy's the given series converges. That's it. Okay. So since here L value is less than 1. Okay. That's it. Right? Next one. Similarly, Problem number 4. Find the convergence status of the series where n is running from 1 to infinity. So here an is n plus 1 whole to the power of n. Again, power n terms are present, so n through test may be most suitable method. See, it doesn't mean that you have to apply only n through test. It is not like that. It is most suitable method. That's it. You can apply any other test also, no problem if it is applicable. But here it is most suitable. Directly you can apply. So now limit n becomes large, nth root of an. So this is limit n becomes large. Okay, n plus 1 power n upon n to the power of n into n I am writing. This one I am simplifying. N to the power of n into n, right? N to the power of n plus 1 means this one. And whole to the power of what? 1 by n. Nth root, right? Nth root means 1 by n. Okay. Now this will be limit n becomes large. Limit n becomes large. Apply 1 power n to both numerator and denominator. So therefore n plus 1 only will remain in the numerator, because n cancel out. This n and this n cancel out. And same 1 by n to apply this denominator, n power n whole power 1 by n whole power 1 by n into n power 1 by n, n power 1 by n. And again here, so this n cancel out. So what remains again? So this will be limit n becomes large, n becomes large. Numerator is n plus 1 and denominator is n into n to the power of 1 by n. Okay. Now this is, so limit n tends to infinity. You simplify the terms. So this is n plus 1 by n, isn't it? N plus 1 by n into 1 by n power 1 by n. There are two terms. Okay, n power 1 by n is one term and n plus 1 by n is another term. And simplify this. So limit n becomes large. Limit n becomes large. So 1 plus 1 by n. Whole power n is not there. If it is whole power n, then it is e. Power n is not there. Okay, don't get confused. So 1 upon n power 1 by n. N power 1 by n. So now you can apply the limits for this. Then we'll get the second term will be 1. So this value. Okay. So then directly. So therefore, what are the limit values now? So first one, 1 plus 1 by infinity into 1 by 1, because limit n tends to infinity, n power 1 by n value is 1. Okay, and this value is 1. Now this is L value, right, which is equal to 1. So therefore test fails. So therefore the test is inconclusive. The test is inconclusive. Inconclusive. That is we cannot decide. Its meaning is that we cannot decide its convergence status. Its convergence status by what? Nth root test. Its meaning is that nth root test. So therefore, but what I want question is find the convergence status, right? Look at the question. The question is find the convergence status. So compulsory we need to find the convergence status. Okay, if the question is find the convergence status by using Cauchy's nth root test, then up to this it is enough. Up to this it is enough. But question is not like that. Whatever the technique you apply, but compulsory we want convergence status. Okay, so by Cauchy's nth root test we are unable to decide the convergence status of this series. Therefore, we move on to the another test. That's what another test is. So let me apply. So first here, what is an? So an is nth term. What is an? Let me go back. So n plus 1 whole to the power of n, right? So n plus 1 whole to the power of n upon n to the power of n plus 1. Okay. Now I want to apply ratio test. Whether it can be applicable or not. Check once. Actually, ratio test is most suitable if factorial terms are present. But here, since the nth root test is failing, that's what we are move on to the another test. That's what one of the test is ratio test. Whether it is applicable or not, we will look on this. So n plus 2 whole to the power of, wherever n, there you write n plus 1. So n plus 1 plus 1, n plus 2, power n plus 1. Power n plus 1 upon n plus 1, instead of n I am writing n plus 1, power n plus 2. Power n plus 2, that's it. Now limit n becomes large. What is the ratio? an plus 1 upon an. Okay. Now this is, so limit n becomes large. Now what is an plus 1? So n plus 2 power n into, I'm writing separately, n plus 2 power n into n plus 2 again, right? Because power n plus 1 is there. If you simplify this, we get again power n plus 1 will get divided by, this is also same, n plus 1 power n into n plus 1 power 2. This is a n plus 1 is over, and divided by an means this one, so this become n power n into n divided by n plus 1 power n. Okay, now we cancel out the similar terms. So n plus 1 power n, no, n power n, no, anything get cancelled, you can cancel out. Okay, so then it becomes, then so limit n tends to infinity. Okay, you take out n power n common from the first bracket, n power n, so 1 plus 2 by n power n, okay, into 1 n common, so 1 plus 2 by n, okay, and divided by, here n power n common, n power n is common, 1 plus 1 by n power n, okay, and here n square is out, then 1 plus 1 by n power 2, that's what n square is out, and here n power n into n, and here denominator n power n will common, so 1 plus 1 by n whole to the power of n. Okay, then similar terms you can cancel out, so n power n is out, okay, and n power n is out, and n into n square, right, n square, and this n square is out. So what will remains after applying limit? So numerator will be e square into this is 1 plus 2 by infinity, that means only 1, right, and denominator e power 1 into 1 plus 1 by infinity power 2. Okay, that's it. Here instead of n I am writing infinity. Next this one e, is it, check once, e, so again e into e square. Okay, so e into e square, so this is out, and again what you are getting, which is equal to 1 you are getting, again ratio test also fails, L is equal to 1, therefore ratio test is inconclusive. Ratio test is inconclusive. Then, so like this you keep on verify actually. Then you move on to the limit comparison test. Okay. So the ratio test is inconclusive. Then I am moving to the next one, limit comparison test. Okay. Next come to the limit comparison test. So for the limit comparison test, what do you want first? So an is, in the term of the series is n plus 1 whole to the power of n upon n plus 1 into the power of n plus 1. How to choose bn? Let bn is maximum n power you have to choose, right? Here maximum n power n I can take common in the numerator, and denominator maximum n power n into n only, right? Same, this I can take common, maximum n power n plus 1 I can take common, so overall this is 1 upon n. Okay, because these two will be cancelled out, n power n and n power n will cancel. Let us choose bn is 1 upon n, then proceed. So what do you want here? So therefore limit n tends to infinity, okay, an plus 1 by n. I'm proceeding by limit comparison test. Okay, so n plus 1 power n plus 1 power n divided by n power n plus 1. Okay, n. So So divided by an. An is n by 1. Okay. And keep on simplify this. So this will be, yeah. So numerator n power n I can take common. So inside 1 plus 1 by n whole power n. Okay. Into n. Next denominator n power n into n into 1. Then cancel out the similar terms. N power n is out, and n out. So therefore, you write limit n tends to infinity, and here also limit n tends to infinity. Limit n tends to infinity. Yeah. Simplify. Now you will get it is e. 1 plus 1 by n whole power n is e. E value is how much? 2.73. For the by limit comparison test, limit comparison test, both converges or diverges together, right? The limit comparison test, but series an and series bn converges or diverges together. Okay. So for that, what I am doing is, so then you find what is uh, series bn status. So series bn is, here 1 upon n. This one is diverges by p series test, So therefore series an is also diverges. That means the given series is diverges. So therefore final conclusion is the given series is diverges. So look at, if L is one, we are struggling like this. Concluded this by using limit comparison test. So therefore, by limit comparison test, the given series is diverges. Okay. Next one. So for what positive values of x the series is converges? Again, look at power n is there. Therefore, nth term test is most suitable. So directly, so limit n tends to infinity. Okay. So nth root of an. Directly I am writing. Hope you will understand. So limit n tends to infinity an. So 2x power n and n plus 1 power n plus 2 power n. So this is an and whole power 1 by n, because nth root test we have like whole power 1 by n. Okay. Now this is, so limit n becomes large. Yeah. So 2x power n and whole power 1 by n. Power 1 by n I am writing separately into n plus 1 by n plus 2 power n and whole to power of 1 upon n. I am applying the power 1 upon n separately. So now here this n and n cancel out, and here also this n and this n will cancel out. So what left? So limit n becomes large. So 2x into n plus 1 by n plus 2, that's it. N plus 1 by n plus 2. Okay. So now limit n is reaching, right? So here only n is variable, therefore 2x is out of the limit. So therefore write 2x outside. Only n times you have to write inside, right? Everything will become constant. So limit n tends to infinity 1 plus 1 by n. N I am taking common in the numerator, and denominator also n common. So that n will be cancelled out from both numerator and denominator. So this will be 2x into limit value is 1. So finally this is 2x. But what is this? This is L. So this is L, limit value. Okay. Then let us look into this. For what positive values of x? Remember, if x is positive, these terms are always more than or equal to zeros. then only I can apply nth root test. That you should take care. Okay. So since an is more than or equal to 0, then you are applying this test. Compulsory to verify. If an is not more than or equal to 0, then you should not apply nth root test. I am not verifying this, but you have to verify actually. For each and every test, you have to verify compulsory. Okay. So that's what for positive values of x. If x is negative, this term becomes negative. Therefore, you cannot apply nth root test. That's what positive values of x question. Yeah. So now here L value is 2x, but when it is converges if L is less than 1, right? So if L is less than 1, right? So if L is less than 1, then the series converges. The series converges by nth root test, by Cauchy's nth root test or simply nth root test. So therefore, what do you want? 2x, which is L, which is less than 1. That means what? 2x should be less than 1. That means your x should be less than half. Since x is positive, so that implies 0 less than x less than half. Okay. Now you have to verify at 1 by 2 does the series converges or not, because at the end points you have to verify. So till this I can conclude by using nth root test. At the end points you have to verify again. Okay. So therefore at the end points, case 1 end point is if x is half. If x is equal to half, then what will be limit value? L is equal to 2x. That means 2 into half. X is half I am taking. So which is 1. Therefore test is inconclusive. Therefore which test is inconclusive? Root test is inconclusive. Therefore nth root test is inconclusive. Nth root test is inconclusive. Then we have to move on to the another test. Inconclusive. Okay, inconclusive. So use any other method to conclude the convergence and divergence status of the given series. So what is the series now? So series an, which is series 2x power n. Okay, and what is given here? Let me go back. N plus 1 by n plus 2. Okay, so n plus 1 by n plus 2 power n. And if you substitute x is half here, x is half, 1 power n will get simply 1 only. So only n plus 1 by n plus 2 power n will get, where n is running from 1 to infinity. Now you have to look at this test. Okay, so this series you have to consider. Now let us move on to the nth term divergence test. Whatever the technique you apply, whatever the test you apply, but you have to find this convergence status of this series at x is equal to half. Now for this test, so limit n tends to infinity, n plus 1 by n plus 2 whole to the power of n. This will be, so limit n tends to infinity. Okay, n power n is common in the numerator, so therefore what will get? 1 plus 1 by n whole to the power of n divided by denominator also n power n is common, then what will get? 1 plus 2 by n will get 2 by n whole power n. Okay, which is, yeah, so n power n is out, so both will be cancelled out. So here n power n and n power n is out, and this is e, right? E by e square. So directly, so this will be e by e square. E by e square. E by e square is 1 by e, so which is not equal to 0. So therefore, by nth term divergence test, nth term divergence test. Okay. All the test you have to remember compulsory. You have to play with it. Otherwise, they will play with you. Okay. The nth term divergence test. The given series diverges. The series diverges. The series diverges for x is equal to 1 by 2. So therefore, what is the final conclusion? So therefore, final conclusion is so therefore, finally, for 0 less than x less than 1 by 2 only the series converges. Because x is equal to half, it is not converges. If it is converges at x is equal to half, I will let less than or equal to like this. But it is not converges, right? Only the series converges. The series converges. That's it. Okay. Yeah. Next one. Next, theorem number 11, Raabe's test. Okay. In this, the requirement is let an be a series with an more than 0. Again, requirement is an should be more than 0, positive terms, such that limit n tends to n into an by an plus 1 minus 1. This value is L. So this limit you have to compute first. L if first conclusion, the series converges if L is more than 1, it is reverse. Okay, L is more than 1, it is converges. If L is less than 1, the series diverges. Again, same, if L is 1, the test is inconclusive. Okay, look at this problem for this solution. So here an and an plus 1 I want. So for that you write first what is an. So an is nth term of the series 1 into 3 into 5 into up to so on 2n minus 1. So here no need to worry because nth term already given. In some of the problems if nth term is not given we have to construct the formula. Okay, 2 into 4 into 6 up to so on 2 into n. And this is an. Okay. Now what is an plus 1 next term? So this is nth term, next term is n plus 1. Instead of n, you substitute n plus 1. So what will we get here? So let me write here first. So 1 into 3 into 5, 1 into 3 into 5, up to so on. Yeah, let me write that. So 2n minus 1. So 2 into n plus 1 minus 1. So instead of n, I am writing n plus 1 here. So 2n plus 2 minus 1. So 2n plus 1. So here 2n minus 1 and what is the next term? 2n plus 1. Is it 2n minus 1? So 2n plus 2, 2n plus 2, so 2n plus 1, 2n plus 1. So next term divided by denominator 2 into 4 into 6 up to so on 2n. Instead of n, you write n plus 1. Then 2n plus 2. N plus 1, so 2n plus 2. Simple. Okay. Instead of n, you write n plus 1. So 2 of n plus 1. That means 2n plus 2. What is the before term? 2n. Then before term is 2n. So you take one exercise here. Apply ratio test. Ratio test. You take it exercise. Take it exercise. You will get L value is 1. L is equal to 1 you will get. Therefore the test is inconclusive. Then we will move on to the Raabe's test. Okay. You try this, you will get definitely limit value 1 you will get. Ratio test. Okay. So therefore then let us apply Raabe's test. For that I want what is an by an plus 1. First to compute this, then I will substitute back. Okay. What is an? 1 into 3 into 5 into up to so on 2n minus 1. Okay. Divided by 2 into 4 into 6 into up to so on 2n. This is an divided by an plus 1 reciprocal. So 2 into 4 into 6 into up to so on 2n into 2n plus 2. 2n plus 2 divided by this is 1 into 3 into 5 into up to so on 2n minus 1 into 2n plus 1. Isn't it? Check once. 2n plus 1. Now let us cancel the similar terms. So up to 2n, all these terms will be cancelled out. Up to 2n. So up to 2n, all these terms will be cancelled out. And up to n, 2n minus 1. to 2n minus 1, all these terms will be cancelled out. Okay, what will remains now? So this will be, so numerator only 2n plus 2 remains and the denominator 2n plus 1 remains. Okay, now let us move on to the limit value. Limit n tends to infinity, n into an by an plus 1 minus 1. So this value I want. Okay, so this is limit n tends to infinity, n into, yeah, what is an by n plus 1? Simply 2n plus 2 by 2n plus 1. This is an by a minus 1 and an by an plus 1 value, and this value I want. So limit n tends to infinity. Okay, take LCM inside. So n is outside and inside LCM is 2n plus 1. So that difficulty we can remove. 2n plus 1. So 2n plus 2, 2n plus 2, and here minus 2n minus 1. So take LCM. And now such a difficulty we overcome. Now look at minus 2n plus 2n is out. So minus 2n plus 2n is out. 2 minus 1 is 1. So 1 by 2n plus 1. Now it's perfectly alright. So now limit n tends to infinity, denominator you take 1, n is out. So n into 1 by, if denominator 1 is, n is out, then what is that? 2 plus 1 by n. 2 plus 1 by n. So now this n is out. n and n is out. Then what do you get? Limit value is 1 by 2. So this is L value, right? And this is less than 1. 1 by 2 is less than 1. Therefore, by Raabe's test, therefore, by Raabe's test, the series diverges. The series diverges. That's it. Because it is more than, it is less than 1, right? If it is more than 1, then it is converges. So therefore, the given series is diverges. Simply, you need to compute this one. That's it. Nothing else. Okay. Next one. Next one, alternating series. So far what we have seen, only series with positive terms we have seen. Non-negative terms or positive terms we have seen. Now we are going to discuss the series with negative terms also. Alright. First one, definition. A series in which the terms are alternately positive and negative is called an alternating series. Examples, look at the first one. 1 minus, first term is 1, second term is minus 1 by 2, third term is 1 by 3, minus 1 by 4, like that. Alternatively plus minus. Look at a series in which the terms are alternatively positive and negative. Alternatively positive and negative. It doesn't mean that first positive. You can get first negative also. Look at the second series. First term is negative, second term is positive. Next negative, positive, like that. Look at positive, negative, like that. Alternatively positives and negatives. And all these three series are said to be alternating series. Okay, alternatively positive and negative. Such kind of series is said to be alternating series. So in that theorem number 1, Leibnitz test or the alternating series test. So statement is this: series n is running from 1 to infinity, minus 1 whole to the power of n plus 1 an. That means what? First term is a1, second term is minus a2 plus a3 minus a4, like that. So terms are alternatively plus and minus like this. Then the series, such kind of series is converges if an should be more than 0. Only an, nth term you take without sign. Without sign you take only an. Okay, that should be more than 0. And second condition need to be satisfied. That sequence is decreasing sequence. If this is an, that should be decreasing sequence. And third term is limit intensity an should be more than 0. Then if these three conditions satisfies, such kind of alternating series will be converges. Related to that, let us find the show that the alternating harmonic series, this harmonic series, right? If I write this one, this is alternating series, harmonic series, but here terms are alternating, so this is alternating harmonic series. Okay, show that this is converges, right? So since the terms are alternating, so therefore we may go to the Leibnitz test. So first test in this is Leibnitz test. If the terms are negative, in that the first test is Leibnitz test or alternating series test. So what is the series now? Series minus 1 raise n plus 1 by n, where n is running from 1 to infinity. Look at the terms once. If n is 1, you will get 1 by 1. Minus n is 2, it is negative 1 by 2. If n is 3, 3 plus 1 4, minus 1 whole to the power 4 is plus 1 by 3. n is 3 I am substituting, n is 4 minus 1 by 4. Look at the terms are alternatively plus and minus up to so on. Terms are alternatively plus and minus. So this is alternating series. Then go to the Leibniz test. So according to Leibniz test, so now let us compare this series with n is running from 1 to infinity minus 1 whole to the power of n plus 1 into 1 by n. So compare this with series n is running from 1 to infinity minus 1 whole to the power of n plus 1 into an, isn't it? So minus 1 whole to the power of n plus 1 is alternating, and 1 by n, instead of an we are having 1 by n. So compare with this, because look at the Leibniz test. Look at the Leibniz test. What is the Leibniz test? Look at minus 1 whole to the power of n plus 1 into an. So in this I am expressing the given problem. Okay. So therefore, instead of an, so therefore, what is an now? An is 1 upon n. Whether three conditions are satisfying or not, one by one you verify. First one is what? An should be more than 0. An is more than 0. Yes, correct, verified. And second condition what? It should be decreasing, right? So n plus 1 is always more than n. It is true for all n belongs to natural number set, isn't it? So therefore 1 by n plus 1 is always less than 1 by n. So if an is 1 by n, what is an plus 1? It is 1 by n plus 1, right? Instead of n, you write n plus 1. Therefore, 1 by n plus 1 is nothing but an plus 1. So this is an plus 1 is less than an. Means what? That implies what? An is more than an plus 1. That means what? It is decreasing sequence, satisfied. And third condition, limit n tends to infinity. Limit n tends to infinity. An value should be 0. Let us compute. If it is not equal to 0, then third condition is not verified. Therefore, by Leibniz test, the series is diverges. Okay. So limit n tends to infinity. What is an? 1 upon n, which is equal to 0. Satisfied. So therefore, conclusion is by Leibniz test. So therefore by Leibniz test, the given alternating harmonic series, okay, converges. That's it. Okay. Similarly, next problem number 2. Examine the character of the series. Okay. Yeah. Again, it is an alternating series, right? Since it is alternating series, then we may move on to the alternating. First test is Leibniz test. N minus 1 upon 2n minus 1. If you want to look at the terms, first if n is 1, 1 minus 1 0, this 1 by 1 by 1. First term is positive. Second term, substitute n is 2, 2 minus 1 1, so negative. 2 by n is 2, right? 4 minus 1 3, 2 minus 3. Next plus substitute n is 3, 3 minus 1 is 2, minus 1 whole square is plus 1, so n is 3. So 3 by 3 to the 6 minus 1, 3 by 5 minus up to so on. So look at terms are alternatively plus and minus. So it is an alternating series. So then again same story. Here what is an now? So an is, without sign you take, without sign simply n by 2n minus 1, n by 2n minus 1. Okay. So then go to the Leibniz test. So directly you go for third condition without verifying first two. So limit n tends to infinity, an value. What is this? So limit n tends to infinity, n by 2n minus 1, n by 2n minus 1. How much it is? So limit n tends to infinity. Let us take n common from the numerator, and denominator is again n common. What will get? 2 minus 1 by n. So numerator will be n. Okay, 1 into n. So this is okay. So this n and n cancel out. So finally what will get? So you will get 1 by 2. But I require it is 0, right? But it is not equal to 0. Test. Therefore, by Leibniz test, the series is diverges. That's it. Because three conditions are not satisfied. If one of the condition is not satisfying, then it is diverges. The series is diverges. The series is, so no need to verify first two conditions. The series is diverges, that's it. Okay, because third condition is not satisfied. No need to verify first and second. That's it. So by Leibniz test, the series is diverges. Which series? Alternating series is diverges. That means the sum is either plus infinity or minus infinity. Plus or minus infinity, because it is alternating series. Okay. So next one, look at this. Examine the character of the series, again alternating series. You write series n is running from 1 to infinity, minus 1 raise n minus 1, okay, divided by root n. What is this again? Substitute n is 1, so first term is 1 by root 1, 1 by root 1, and second term substitute n is 2, 2 minus 1, so minus 1 upon root 2, n is 3, so 3 minus 1, 2, minus 1 whole square is plus 1, so 1 by root 3, next minus 1 by root 4, plus up to so on like this. Look at the terms are alternating plus or minus, therefore it is an alternating series. So therefore clearly you pick up what is an. So without sign you pick up, that is 1 by root n. 1 by root n will be an. Okay. So now what is an plus 1? It will be 1 by root n plus 1. 1 by root n plus 1. Okay. Now let us verify 1 by 1. First one is what I want, an should be more than 0. So an clearly more than 0, right, for all n. So first condition is satisfied. And second condition what I want, it should be decreasing, right? Yeah. So start with n plus 1. So n plus 1 is more than n. It is true for all natural numbers. All n belongs to natural number set. And so therefore root n plus 1 will be again more than root n. It is true again. So 1 by root n plus 1, 1 by root n plus 1 is less than 1 by root n. 1 by root n. So therefore this is an plus 1 is less than an. So therefore clearly n is decreasing, satisfied. So third condition, limit n tends to infinity, limit n tends to infinity. What is an value? So limit n tends to infinity. What is an? An will be 1 by root n. So that will be 0. So third condition also satisfied. So therefore conclusion is, so therefore by Leibniz test, by Leibniz test, the series is what? Converges. The series is converges. That's it. So the sum will be finite. Previous problem, the sum is not finite. It is plus or minus infinity. That means it is diverges. So with this I will stop.